Okay. So, nice to see you guys. Glad to see we still have some people left, despite the usual useless last couple lectures of the course. Let's see here. In terms of announcements, things were pretty straightforward. So essentially there is a lecture today, there's a lecture on Thursday, and then my job here is done, and it's on you guys. So on Tuesday, you'll all be giving your practice, or not your practice talks, your actual talks, which is practice for real life. So don't forget that for your project deadline. Again, you cannot use the late day, like the course late days for these things. That's not a thing at the end of the semester. So please make every effort to finish your project on time so I don't have to deal with a bunch of special case grading things. And then other than that, you have a project report due. Any questions, comments, concerns? I think logistics get monotonically easier between now and the end of next week. Okay, fantastic. Sounds good. So in that case, I guess we'll get started with our technical content for the day. So today we're going to continue our discussion of correspondence problems, which is, I guess, going to be the last topic in this course, given how slowly we're talking this time, which is great, because these are problems I know about. And essentially, we're going to expand our consideration in today's lecture. In the previous lecture, essentially we considered this problem where your input was a pair of shapes, and then your output was a mapping from one into the other. That was like low distortion, or like, didn't stretch one onto the other too much, and so on. And we talked about a lot of different models, both for optimizing for these, different objective functions you might use, and so on. But the reality is, oftentimes, we have more than two shapes, and the question is, what do we do in that situation? And we're going to kind of explore some of the mathematics that comes up in this idea of consistency, and this, which originally arose actually in the geometry community, and then became extremely popular in machine learning community, where they kind of glued the word cycle onto the beginning of it, and we'll see essentially where this shows up in practice. So probably today, we'll start by doing the mathy part of consistency, and if I get my timing right, by the end of tomorrow, we'll talk about how that has some influence on machine learning models. So essentially, in our previous lecture, we had an input that looked something like what we see here, right? So we had maybe a horse and a donkey here. There's some shared structure, and what we wanted to do is find like a smooth mapping that takes in points from one of these shapes, outputs points on the other shape. And then once we have such an object, we can do things like transfer texture from one to the other, or labels, information, what have you. But the reality is, in modern geometry application, we typically don't just have two shapes, we have an entire collection. So maybe we have a horse, a donkey, giraffe, and a zebra. And now, if we take our mapping tool that we developed in the previous lecture, we can take any pair of these shapes, and we can compute a map in between them. And in particular, for fun, we could do an exciting experiment, which is essentially what I've illustrated on the screen here, where I'm going to use my software to compute a map from the horse to the donkey, and another map from the donkey to the whatever that is, to the giraffe, another one from the giraffe to the zebra, and then finally I'm going to run my software a fourth time to map the zebra back to the horse. And now what I could do is I can take those four maps and I can compose them together, and I can see what I get. Right, and I think there's a reasonable question you might ask. So now we have sort of a cycle. We think of this kind of like a graph where every edge is decorated with a mapping. Then essentially what we've done, we've composed around the cycle, and you might ask, well, what do we expect to happen? And I think, there's a lot of different answers to this, but in some sense, philosophically speaking, like in the absence of any reason not, if I took all these maps and I composed them together, horse, donkey, giraffe, zebra, and back, I'd probably expect to get the identity map, right? That feels right. The question is that really what ends up happening? So if I actually take almost any of the software tools that we talked about in our previous lecture, all of those tools input two shapes at a time and compute a map. If I compose them all together into a cycle, what do we think is likely to happen?
You get some distortion.
Yeah, you get distortion. Likely you get garbage. At least one of the maps might just be wrong. It could be that they distorted in different ways. There's non-unique ways to map from one shape into another. And these algorithms are just not designed to be consistent in any fashion. In fact, even the mathematics of mapping isn't really designed that way. So for example, if I compute what's called a harmonic map, like I solve Laplace equals 0, a map from A to B that is harmonic, if I take its inverse, is not harmonic. So the inverse of a harmonic map is not even in the same space. So the mathematics here are quite complicated. And the takeaway is that by default, these mapping algorithms, the way that we've described them so far, are not cycle consistent. Cycle-consistent would mean that I have a mapping tool that takes in a collection of objects, computes maps between every pair. Now if I compose in any cycle, I get identity. And that's actually a really hard constraint to enforce in practice. To my knowledge, there aren't any interesting pairwise mapping algorithms that are cycle-consistent. And so this is a thing that I think people have studied in many different contexts. Because in some sense, I mean, it's a little hard to phrase this, but in some sense, there's almost a philosophical point, which is like, if your mapping algorithm, like any of the ones we talked about in the previous lecture, isn't cycle-consistent, you should kind of ask yourself why, right? Like, is that a property that you expected, or just like a byproduct of a bad algorithm? And I would say 9 times out of 10, it's the latter, right? Like, we don't actually really have a great explanation for why these tools shouldn't have this cycle consistency property if really they're trying to compute some like God-given ground truth, nice map that we think exists in our model, right? Yes?
Wouldn't you have an issue with symmetries where you get the cycle and get back to...
Absolutely, yeah. So symmetry can cause a problem, noise can cause a problem, distortion can cause a problem. All of these things cause issues with cycle consistency. Absolutely.
Okay, but that wouldn't necessarily be something your algorithm's doing wrong, right? The zebra to the horse.
That's right. Yeah, in that case, like maybe you say, oh, it's not fair. Like my algorithm doesn't have the information it needs to be cycle consistent. That's absolutely right. Now, in the case of the zebra, there actually would be a way to fix that, which would be to consider some extrinsic information, right? Like, you're right, these algorithms that depend only on the Laplace operator can't distinguish left from right, but obviously we can in everyday life, and that's because we're embedded in 3D, so maybe that's just not the right mapping algorithm for that data, right? In fact, actually there are algorithms out there that break that symmetry and otherwise remain intrinsic. There's some interesting work in functional map literature that does exactly that. But yeah, I mean, essentially, like when your maps are not cycle consistent, somehow you've learned something interesting about your mapping algorithm. And sometimes it's something interesting about the algorithm, and sometimes it's interesting about the model. And a lot of times you might say, well, maybe I can go back and take a collection of maps and fix it, and that's sort of what we'll try to do today for the most part. And so, by the way, incidentally, if you're like a mathematical philosopher and you want to think about a really hard problem, you might remember that we talked about one notion of curvature is holonomy, right? This is on your homework, where like I do parallel transport, I kind of move something in a cycle, and then I get back to something that wasn't what I started with. You might kind of look at this structure here and say, like something is kind of similar to this, right? I do mapping pairwise, I go to cycle, and I don't get back where I started. I think there's some really interesting kind of mathematical modeling to be done. Like, is there curvature in the space of shapes? And if so, like this would be one way to sense it. But I digress. Now, why is it that our mapping algorithms are not cycle consistent? Like, let's say that ahead of time, a priori, I had my entire data set. So I don't need to run mapping pairwise. I could take all of the maps and kind of consider all the shapes at the same time. That feels like it should make cycle consistency somehow easier, right? Like, at least you kind of know your enemy. But the reality is that cycle consistency is a really gross nonlinear constraint to deal with. Right? Like, you're looking at the composition of maps where the maps are your variables in your optimization problem. And so from this perspective, it's really pretty clear that like the reason that algorithms are not cycle consistent unless they're kind of trivially so is that this is just a constraint that's hard to work with. There's one exception, which is that it's very easy to be cycle consistent if you write all of your maps as the map into one shape and then out of one shape, right? This technique, I think we'll see it later in these slides, but just so I don't forget, sometimes they'll call this an Ur shape. Thank you, Marcel, for this nice chart. So essentially the idea here is that like I have a bunch of different objects, whatever they are, maybe they're medical image scans, whatever, and essentially my mapping algorithm's job does not take a pair of shapes, it actually just takes one shape at a time and maps it to some canonical domain in an invertible fashion. Then I can get a cycle consistent algorithm very easily by just saying, okay, map from A to B is I map A to canonical shape and then back out, right? That's pretty much the only model we have. So indeed, actually in the medical imaging community, this isn't all that uncommon, which kind of makes sense because it's a little bit easier to come up with like an average organ than it is like an average, four-legged animal. But both of these are extremely squishy topics. That literally, it's hard to work with. I see that. I mean, moreover, adding cycle consistency is also something you might want to do in like a soft way. So it's also kind of important to think about that mathematics in this fashion. Like maybe this is something you want to push your mapping algorithm towards satisfying, but not 100%. Or Chip?
I just didn't quite get why is it easier to achieve cycle consistency in this?
Oh, because here it's built into your model, right? There's no way to have a mapping algorithm. Like if your map is always, I've always mapped to the same shape. Like I just have one fixed archin in my database sitting like that, and I map everything to him, and then back out, right? Then they're all cycle consistency, but consistent by definition, right? Because they all, the map from A to B, the map from A to C, no matter what, they all just compose through the center guy.
But then I can be assumed that maps to the average shape, they're perfect. Maybe.
That's right. So you better hope that you can find a good one. Yeah. Which is why that model is maybe not so great. So there's somehow two different conflicting views, right? Like on the one hand, cycle consistency as an optimization constraint is really hard to work with. This is an annoying thing. It's like multiplying matrices a bunch of times. On the other hand, somehow, from a high-level perspective, I just gave you like 3 shapes or 10 shapes instead of 2. I should be able to do better on my mapping problem than if I only had a pair, right? I can start to notice patterns among all the shapes that maybe give me some clue on how to extract a map. And so there's this sort of push-pull. Like on the one hand, I have more information, like more data should help me make mapping easier. On the other hand, if you actually look at the constraint we're trying to satisfy, it's really annoying. and that's the sort of basic push-pull in this literature, that like consistency is a really hard thing to enforce, and there are many models for how to do it, starting from the very rudimentary through very fancy stuff like semi-definite programming, which we'll talk about in a bit. So today, and probably for our next lecture, we'll talk about kind of a sampling of different strategies for consistent correspondence, and they really range in complexity from like the kind of sledgehammer approach like what we see here to some methods that at least try to like detect and remove bad maps in a collection of maps, all the way to ones that'll maybe take a whole collection of maps and then repair them one by one to make them all cycle consistent, but like in a way that preserves the structure as much as possible. And so this is a huge thing. Now, really, I think the holy grail in correspondence literature, and I would argue is still an open problem, is just an algorithm that takes in a big data set of like thousands of shapes, makes a consistent set of maps, they're all low distortion, and it does so in an efficient fashion. Like this is a hard problem, and it's somewhere between machine learning, geometry, optimization, you name it. Like this is just a nasty problem to work on. Okay, so there are many different ways to formulate these different problems. We'll go through a bunch of them, but the one that we'll kind of probably focus on for the most part today looks something like what we have on the slide here, where as input you're going to be given 2 different objects. First, you'll be given a collection of n shapes. If it makes your life easier to think about, you can think of all of those shapes as having the same number of vertices, but obviously that's a constraint we're going to want to relax later. And moreover, between every pair of shapes, we'll compute a map. So maybe we run the algorithm from our previous lecture, and so we have this big set of pairwise mappings that are maybe good-ish, but noisy and not cycle consistent, and we feel like by making them cycle consistent, we can either correct small errors or even fix a few symmetric flipped maps that are bad. Okay, and so our output is going to be aiming for a cycle consistent approximation of that set. That makes sense? And there are many, many, many places where these problems come up. So for example, a very common one, which actually is still a problem people study today, but even goes back to like early 2000s, is in 3D registration. So here we're trying to take a 3D scan of this lawn gnome in like kind of a weird seductive pose here. And we take him from a few different angles. We're trying to register them together. And maybe in this case, the map is particularly simple. It's just between every pair of scans, I estimate a rotation from one scan to the next. But even there, those rotations may not be consistent, right? Like, because they might just be wrong. And so the task, even in this old paper in 2002, was to take all of these views, which were pairwise registered to one another, and then put them all in one coordinate system, right? Now, the way that they phrase this back in computer science land, this is actually it's kind of interesting. Like a little bit before, people were just in the habit of phrasing every problem as an optimization problem, which I think is sort of the default now, was to think of it more like an algorithms thing. So the way they thought about it was I have a collection of shapes. Each shape is kind of like a node. And then we've got a bunch of different edges that form a graph, where the edges are like the directions where I have a mapping from one shape to another. And essentially what they want is the largest consistent spanning tree of your graph. So here the idea being that, like, you know, if I can go from one edge, so as long as there's a spanning tree in my graph, then somehow I have a consistent set of maps by always just composing along the tree, right? I'm just going to throw away the remaining edges here. And so what they were optimizing for was to extract a spanning tree that kind of makes everything look nice. Essentially, what you can you can imagine, I don't even think it's worth going through the details of this algorithm because it's been replaced many times over. This particular technique was agglomerative, meaning that you kind of just like keep gluing vertices onto your spanning tree. And essentially what they wanted was something that was kind of as consistent as possible with all the edges you already chose so far. So you'd like start with one 3D model, you'd find another one that's registered to it, then you find the third one that kind of agrees the best, right? The third map that you haven't added to your set, that agrees well with the current registered thing. You'd add it and do that in a greedy fashion. And I think all of you guys at home could cook up some kind of reasonable set of heuristics for doing something like this, right? So essentially you're just choosing among rotations so that things like don't suddenly get like super misaligned. Now, when you do this, I mean, this is a greedy algorithm, right? And there are actually many spanning trees for this graph. And if you make one bad decision in an algorithm like this, your entire registration algorithm is kind of hosed, right? Because like suddenly, like I'm gluing together this happy sideways gnome, and then I get like one flipped backward map, and then suddenly all the remaining shapes have to decide which one they have to agree with when I add a new edge into my graph, which is not so great, right? And so more modern approaches to this are not greedy, but rather try to optimize in some clever fashion. Or at the very least, before running a procedure like this, try to remove maps that are clearly bad, right? It would be one thing you could do to make things a little better. So if we kind of go through the history of this little research area, and when I say little, it's actually kind of exploded a lot. This was sort of the earliest style technique. Moving forward a tiny bit, people said, at the very least, if I'm going to run one of these spanning tree methods, I should try to remove edges in my graph. So in other words, maps that I can really clearly detect as bad. But the problem is that, like in the consistent mapping universe, if I just give you one map, I can't really evaluate if it's useful or not, right? Like essentially, a good map is one that agrees with all the other maps, right? It's something like a map is made good by the company that it keeps, or some damn thing. So in other words, like when is a map bad? Well, like let's say that I have a collection of shapes, so like a bunch of nodes, and let's say that I have maps on all these edges. And let's say for whatever reason, one of these maps is bad, like this guy. And all the rest of them are okay. Right? Well, unfortunately, when I say bad mapping, I really can't detect it. Like I don't have the option of like locally changing distortion. Like maybe this map is just flipped left to right, like we asked about before. So what can I do? Well, I can start drawing cycles in my graph and composing and seeing if I can get the identity. Right? I'm going to just start doing a bunch of experiments. So maybe, like, for instance, I look at this triangle here, I compose, I get identity, like, good, this is a good cycle. Now I do this one, so this is a check mark, this one's an X, this cycle is an X, and that cycle is a check mark. And so I just do a bunch of experiments of cycles, each of which I compose and see if I get an identity or not. And pretty soon, maybe I start noticing that one of these edges, when it's present in the cycle, consistently leads to bad maps. That's the kind of situation that I'm going to try and detect. But unfortunately for us, the situation can get really complicated. So like this picture is pretty clear. Like there's just one bad edge, and like anytime I compose through it, there's a bad cycle, right? Like that's detectable. But for example, this is just to kind of get you guys thinking about why these problems are so hard. Let's say that I have two bad maps. So I have a big cycle. So think about all those maps between like horses and giraffes and so on. And here's my graph, whatever. It's got my graph is triangulated for no real reason other than I'm drawing it on the board. And I have two edges, both of which, like maybe these are all human models. Accidentally flip left and right. Right? So here's a problem. What happens if I compose through this cycle? How does my map look? Actually, it looks perfectly fine, because I swap left to right, and then I swap left to right again, and these two things cancel out. In fact, if you look at this graph, can I draw any cycle that's going to detect a bad map? No. This is a completely undetectable situation. Right? And so there's sort of happy middle ground in between these two situations, one of which is like very easy to detect, one where it's like literally impossible to detect. And essentially these are the kinds of problems that you can get yourself really caught up in this domain. Does this example make sense? Tim's like looking, he's got questions, this one, I can see.
Also confused to like imagine we have a guarantee that like we checked all cycles of size 3 in this graph, and we know that all of them are good. But then does it mean that any cycle of length 4 or more is also good?
I'm going to let you think about that for a minute. That's a fantastic question. So to repeat our Tim's question, let's say that, so far I've just drawn cycles of length 3. Notice, by the way, in this graph, there's literally no cycle that can detect this bad pair because this has valence 2. I was just lazy. Well, if I had another edge coming out of this, it would be a different situation. Our Tim asked a question, which is like, okay, let's say I check every single cycle of like 3, right? So I look at every single triangle in my graph. Is that sufficient to have an entire consistent set? So for one thing, you would have to assume that your graph has a triangulation, right? Like it does here, but if I did that, now I couldn't check your condition. Conveniently, it's planar here, so you could try and extend it. But yeah, there's a broader question, which is like, if I check all the k cycles, am I done? The answer is no, generically. But under some conditions, yes. And I'll point you toward a paper that articulates exactly that in a minute. So, good thinking. Any other questions? Okay, so next we'll talk about the CVPR paper from 2010. So most of you were in elementary school, where essentially the idea here was sort of halfway in between some of the other methods we'll talk about, where at the very least we're going to try and detect and remove bad maps from my graph, right? Because then when I run the spanning tree, maybe it's still useful because like my maps are like locally a little inaccurate, but like at least they're not like flipping something upside down or something like that. And so here's the way that they articulated this model, is that essentially the first step of their algorithm, like from A to B here, they have this graph of all these matchings, which they compute. And for B to C, they just randomly draw loops in the graph. And I think, like, to go to our Chip's question, often it's sufficient to just kind of randomly draw triplets, but you don't have to. And so essentially, for every single loop that they randomly draw, we're going to make an optimization variable, which is going to say 1 if L is a bad loop, meaning that it contains at least one bad map in it, and 0 otherwise. And similarly, for every map, so like every edge in my graph, I'm going to have 1 for a bad map on graph on edge E, and 0 otherwise. Struggling today. Okay. So, what does it mean to be a bad loop? Well, essentially, and notice that the only thing that we can check here is whether a loop looks self-consistent, right? So we don't ever actually have access to the XE variables, and we probably only have kind of a fuzzy measurement for this guy, right? Like we compose in a cycle and we kind of measure how far off we were from where we started. But what we can do is the following. We can say, okay, well, I've got a bad loop exactly if I have at least one bad edge. So let's assume that we somehow constrain our variables to be binary. We're obviously going to relax that in a minute. Well, then one way to articulate that is to say that, well, XL is greater than or equal to XE for all E in L. Do we see that? Because like, if any E has XE equal to 1, meaning it's bad, then the loop has to be 1 because it's binary and it's bigger than the smallest value in its loop. Does this constraint make sense? Okay. Now, the next one's a little bit more annoying to articulate, which is if all the edges in loop are good, then the loop is good. Well, one way to do that is to say the following, that X loop is less than or equal to the sum of XE, where E is in L. Because again, this only works for binary variables, right? Because now if I go over my loop and all of these things are binary, right, then I'm just going to have a bunch of zeros if all of the edges are good. This thing is also binary, so it's 0 is less than or equal to 0. So then this is going to label this as a good loop as well. Does that make sense? Did I get this right? Yeah, I did. Okay. So this is just a sneaky way to translate a binary program into one that starts to look like linear programming. Okay? So those are going to be basically all we can say about these x variables is relatively little. And so what this old research paper proposed was this problem that's highlighted in blue on the screen, where they noticed that these two constraints are exactly what we just articulated. And then the third one, right, this is a trick that we've seen many times in this class, is we want our variables to be binary, but binary things are NP-hard, they're hard to work with, so we're just going to relax it to be in the range from 0 to 1. And then we're going to maximize the correlation between x, which is our loop score, but it's binary, and there's just some measurement of how inconsistent your maps are, right? Which you could just do compose in the cycle and then maybe measure distance from where you started, something like that. Okay. So what happens in this paper is they run this thing, and then essentially what it's basically trying to do is to attribute, like how these row values are really kind of distributed along the edges in each of the loops, right? That's really what they're aiming for. And while they're at it, they sort of say, like, well, the rows are decimal values. We also want a binary XL while we're at it. And so this is one of the early techniques for studying this consistency problem, which is at the very least to kind of come with a binary variable. Like, I should throw these edges away before I do my tree technique. That makes sense? This is a very easy thing to try. It's a linear program, so it's convex, it's easy to implement. Okay, so unfortunately, that's a nice picture, but algorithms like this one will not detect the situation that we illustrated before, right? Like there could be edges here that are simply undetectable when it comes to consistency versus a second term, which was termed accuracy. The idea being that, like, maps might be accurate or not, meaning they may flip left and right, or they might not, for example. And then they might be consistent, meaning that you compose in cycles, and consistency is a weaker condition, right? And so essentially what this paper articulates is very close to the question that Artem was asking earlier. So I'll encourage you guys to look there if you want the kind of combinatorial argument. So they at least restrict to this is a very restrictive case of the mapping thing in general, where they're looking specifically at permutation matrices. So like all of your shapes have the same number of points, which is a heavy conceit. I think, although actually I'm not sure that's 100% necessary in this paper. Maybe I take it back. I'd have to look. But they sort of want to know, like, a reverse of the question Artem was asking. So a different thing you could ask is, let's say that I detect a bad cycle, right? And somehow I only have 3 options for which of those maps is bad, right? I guess it could be more than one, like if all 3 of them is bad. But essentially what we want to be able to do is to figure out when is detecting just bad triplets enough for either detecting that there's a consistency issue and secondarily repairing it, right? And so what this paper says is they define a kind of funny little condition they call almost accurate for a collection of maps, which says that there do not exist any 2 maps that belong to the same 3 cycle in your graph that are both bad. So in other words, you can never have the case where a 3 cycle cancels out. Does that make sense? And so what this algorithm proposes, they call that an isolated bad map. So it's like one bad map in a big collection, rather than like 2 bad maps that can sometimes cancel each other out. And then they take kind of like a computer scientist approach to how to repair it. Like they have a combinatorial algorithm that kind of starts enumerating triplets, computing maps, trying to detect when they're bad, and then identifying these bad edges and fixing them. By the way, it's very easy to fix a bad triplet, right? Like so if I have A to B to C back to A, and I notice that like this edge is no good, then what they'll do is they'll throw it away and then replace it with the composition of the other 2. So this is a very simple algorithm. They just detect these isolated bad maps, they just remove them, replace them with the composition around the cycle the other way, and then iterate. And they show that so long as you satisfy this condition here, then you'll converge on a consistent set, which is kind of cool. I should note a different way around these kinds of problems, which maybe we won't go into the detail about, is to just relax things and make them fuzzy. Like maybe I just start mapping things 50% over here and 50% over there. Then consistency becomes kind of a tricky matter to measure and to define, pin down, and so on. This was originally developed for this idea of fuzzy correspondences, which played in my office, but Wi-Fi in this classroom is terrible, so apparently we will not see it here. But they have these user interfaces where like you have a whole collection of shapes. You could like highlight a region on one shape and it would kind of show you the region on all the other ones in the collection, which is a useful kind of a tool. And of course for tests like that, it's okay to kind of soften things a little bit. But hiding inside of this algorithm is, again, another kind of fuzzy correspondence technique, which is kind of built on the idea of spectral embedding, actually. So it's built on some of the methods that we've already covered in this course. Since we can't see the video, maybe we won't go through the detail here. So now we're going to start digging more and more deeply into methods that are messier and messier and messier in terms of like they really consider that consistency condition very carefully mathematically and try to articulate optimization problems like guaranteed to have a consistent set of mapping for some notion of consistency. And these things get really hairy really fast. This was a popular topic to study in geometry maybe 4 or 5 years ago, a little bit less so now. But there's still a lot of open problems. I think the open problems just got really hard. So one kind of instance of this problem, which was considered back in 2010, was this idea of consistent segmentation. So here I've got, this is yet another one. So like, for instance, maybe I run my favorite machine learning algorithm to segment a bunch of 3D shapes. So in other words, like identify the legs and the arms and the hands and so on. Then very typically, one thing you might want is like if you have a big collection of shapes, maybe you want to segment in a consistent fashion. So like, in other words, if I'm solving the unsupervised version of this problem, so nobody labels like the arms and the legs, we just have a bunch of shapes, and I want to divide them into somehow consistent parts among all of these things, you can run into some really interesting challenges. So for instance, if you look at this model here, she has a straight leg, and so from the just purely geometric segmentation algorithms that are out there, it's unable to distinguish that you probably want to cut the leg at the knee, but then by the context of the rest of the collection, these two shapes with straight legs then are segmented into having top and bottom just to have consistent in the entire set. Right? That's the kind of problem they're solving. On the teddy bears is another funny example. Like the teddy bears on the left have very small ears. And so normally they won't get segmented out by these automatic tools. But then if you have a whole collection of teddy bears, the rest of which have ears, it'll try to label the first guy. So that's the kind of problem we're solving. Okay, so there are many reasons why this problem is important. For example, you also can have the opposite issue. So like here's this funny sunglasses collection where these things have some cue for shape segmentation. For some reason, there's like a little pinch point here that's kind of irrelevant. And so they want to repair it. Or maybe there's like some structural kind of thing, like this subtle teddy bear ears. And then, range of bears. So, right, so this particular technique, again, I don't think we'll go through all the details because these things just keep getting replaced many times over. It's more just to give you an idea of some of the ways that people go about solving these kinds of problems. What these folks did, which is, I think, a very typical way to translate these problems into something tractable that you could optimize over, is to say, I'm going to over-segment my shapes. Like, I'm going to take my 3D surface, and maybe I'm going to segment it like 50 different ways. Like, I'm going to cut it into, like I'll run some randomized algorithm that sometimes cuts to the knees and sometimes doesn't, and sometimes cuts everything in half. Like, just produces all kinds of different overlapping patches that may or may not be useful segments. And the reason to do that is now you can optimize, now you have a set of optimization variables that make sense, namely a binary variable for each of these little cuts down here, saying, should I use that in my final segmentation or not? Right? And so that's what these folks are after. And so how do they do that? They say, well, every single point on every single surface should be covered by one of these cut objects that we got. You can see, based on this example that we did here, kind of the strategy they'll use for implementing that. And moreover, maybe I kind of make some surface area measurement that makes sure that, my segments aren't all totally tiny. Like, I prefer big segments over small ones, and so on. And moreover, what this paper did, which is kind of sneaky, is they used a bunch of inconsistent maps between all the different pairs of shapes to, at the very least, kind of evaluate, if 2 points are in the same segment over here, do they get mapped to the same segment on the other side? These sorts of questions. And so the kind of sneaky thing in this particular algorithm and many others is that the mappings here they're not variables. They're just constants that you're using to check whether your segmentation is consistent or not, right? So you can look at a point here and its segmentation, a point there and its segmentation, similarly for two other ones. And notice that these are just reading off variables in your optimization problem. And you can just check if they're equal or not. You subtract the two. Yeah. Right, so at the end of the day, what does this thing do? It just wants there to be consistent segmentation and one that at least aligns with the geometric features a little bit. They optimize these binary variables using a very similar trick to what's on the board here. And what comes out is one segment per part. Usually, unless you get bad luck, like remember we had this relaxation where these variables, we wanted them to be binary, but then sometimes they're like 0.5, and then you have to do some rounding. So that's the kind of strategy that's out here. Again, we're rushing through this because this is one of these things that you should understand at a high level. There's like no reason to understand the details because they've been replaced many times over. It's just the kind of approach people use in the early consistent mapping literature was a lot of these like linear programming style methods that were trying to like put ones and zeros on like, are these things consistent? Should they be included in my collection or not? And then sort of solving this thing secondarily. But neither of these algorithms is globally optimal. Like, for one thing, this algorithm didn't even do consistent mapping. It started with maps and it ended with segments. And then the one before is just trying to like label bad maps, but it doesn't actually necessarily give you something binary, nor does it tell you how to repair a bad map. So there's a broader question here, which is whether you can extract a set of consistent maps in some globally optimal way, where we have to decide what it even means to be globally optimal. Like, what is our measuring stick for how well we're doing on a problem like this? So we're going to consider the problem of inputting a bunch of maps between a bunch of different domains. We're going to represent them just as like binary matrices, like permutations. And then what we output is an approximation of that big collection that is cycle consistent. Okay, that's the problem we're going to try and solve. And that one is easy to articulate mathematically. Well, easy is the wrong word, but possible to articulate mathematically. Okay? So, in this conceit, we're going to represent maps in the simplest possible fashion, which is just a permutation. So like, I'm going to assume every single one of the shapes in my data set has the same number of points on it, and that it's just a question of permuting the points of one object onto another. Obviously, this is not a very realistic constraint in application, so this is something you have to relax and think about how to fix. And there actually surprisingly little work out there for taking the model we'll talk about and making it work in that context. This is a good problem for you guys to think about at home. Uh-oh. Okay, so if every map is a permutation matrix, let's do a little bit of linear algebra review. First of all, what is the inverse of our map going to be? What is the inverse of a permutation matrix? Say it louder. Itself. Not quite. Well, yeah, quite. Or you can transpose it, as I think usually the way that we'll think about it. Yeah. Is that right? No, the inverse of a permutation is not itself. So think about taking a set and cycling it around by 1. Then you have to cycle like 3 times to get back. But if you transpose your matrix, I wanted to be agreeable, but I shouldn't have been. The transpose of a permutation matrix is its inverse. In particular, there are orthogonal matrices. Yeah. In fact, I believe a positive orthogonal matrix has to be one of these things. Is that right? I think that's right. Up to sign. Oops. Okay. So unfortunately for us, like binary constraints are no fun, right? Like this kind of thing we can't really do because that doesn't lead to a nice convex program. And so a very typical thing to do is to relax. And so in particular, we're going to consider a very important set of matrices, which is one that you encountered on your homework, but you may not have realized the dire importance at the time, which is the set of matrices whose rows and columns sum to 1. Okay, so in particular, here's the set that we're going to deal a lot with today, which is the following. We can call it, I don't know, doubly stochastic, or n, equal to the set of matrices, which are in R n by n, and satisfy that they are positive. This is like in the entry-wise fashion, that their rows sum to 1, and that their columns sum to 1. Okay. Now, first of all, do we all agree that permutation matrices are within this set? Because remember, like in every row and every column of permutation, there's like 1, 1, and then a bunch of zeros. We agree? Nods, acknowledgement, something. Thank you. But this is a bigger set, right? Like, so for example, the matrices are like all 0.5s or something might be in there. Yes, Archana?
Yeah, just like, why should it be semi-positive definitely?
It shouldn't be. This is an entry-wise positive.
Oh. Okay.
Yeah. Certainly we agree that this is entry-wise non-negative. Yeah. Okay, good. Yeah. PSD wouldn't really make sense because it's not symmetric. Yeah. Any other questions? So this is called the doubly stochastic polytope. It forms a weird shape in n squared dimensional space. The corners of that shape happen to be the permutation matrices, which is a convenient property to have. And it's one that you see all over the place in the mapping literature because this is the convex hull of the set of maps, right? This is like sort of the smallest convex set that contains the permutation matrices. Okay. All right. So here's going to be our basic setting for our optimization problem is the following. Did I manage to get it right already? No. So I'm going to repair slightly and call that M. Sorry. So we're going to have n objects, and each of our objects is going to have m points each. So the reason I just repaired my notation a little bit is that I'm going to think of my maps as m by m permutation matrices. Does that make sense? Okay. And so essentially what we're going to be given is a big collection of m by m matrices between every pair of shapes. We're going to relax that a little bit later. And then what we're going to try and output is a consistent approximation of that set. Meaning that we're going to try and keep as many of these entries the same as the input as possible. That sound reasonable? I think so. Okay. Right, so here's our to be a little more formal about it, this is what it looks like. We're going to have this giant matrix. So let's say that we have so I'm going to continue to establish a little bit of notation. Everything in this universe is really annoying because there's going to be a lot of indices, and the order of the indices is going to be hard to remember. So for example, here's a good one. So I'm going to say phi ij is equal to the map from I to j. Okay? But what does that mean? That means phi ij of x. What space should x be in? So if I write some notation is x on shape I or shape j? I. That's right. And so this is going to be really annoying to type check because there's like an index that's going to be in between things. So just keep that in mind and keep me honest through the lecture because chances are I'm going to flip indices backward. Because for example, what you'd like is phi ij composed with phi jk, but that actually is wrong, right? You can't do that. Okay. And we're going to say that we can make x is going to be this matrix of all our maps. And essentially what that's going to mean is that it's going to have little m by m blocks inside of this thing. And so overall, it's going to be in a really big space. It's going to be in 0, 1 to the m n by m n. And it kind of looks like this. It's got little, m by m blocks in it, each of which is the map from one shape onto another. Does that make sense, what this is? So these are lots of little permutation matrices. Okay? All right, so we're going to make some assumptions on our map collection. So essentially, what we're going to say is that we're going to define a set of map matrices, like x's here, to satisfy a few properties. Here's going to be the map matrices. Let's see if we can fit it into this corner here. One is that they're going to be binary. So in other words, every point just gets mapped to every other point, just 1 or 0. 2 is going to be that the diagonal, what should the diagonal blocks of this X matrix look like? First of all, what are the diagonal blocks? They're maps from something onto itself. So what do we think the permutation should be? Yeah, just the identity, right? So this is just if we, in our little schematic here, they're being little identity matrices sitting down diagonal. Okay, so the diagonal is going to be identity m by m blocks, like that. Okay, and then 3, all of the m by n blocks are doubly stochastic. So notice that 1 and 3 together mean that basically there's a bunch of little permutation matrices. Does that make sense? So when I use the phrase a map matrix, this is what I mean. The matrix of a bunch of permutations, and the diagonal of this thing is a bunch of identities. Okay. So this is the set that we're going to worry about a lot today. So, first of all, let's say that I have a collection of maps, like this X matrix here. This is really big. It's Mn by Mn, big matrix. And this is a perfectly consistent set of maps. Right? They satisfy my cycle consistent property. So I can go like A to B to C, B to B to A, and back, and life is good. What should the rank of this matrix be? This is a good linear algebra puzzle. Let's think about it for a minute. Full rank. That's one possibility. But the fact that I'm asking this question indicates it's probably not the answer we're looking for. I don't know, Justin. Yeah.
It should be the rank of one, like the rank of big M matrix.
Okay, so now we think it should be the rank of this one of these objects. What is the rank of that, by the way? It's just a little m, right?
M minus 1 squared.
M minus 1 squared.
The minimum of N on N.
What was that?
The minimum of N and M.
No, I think the rank of one of these blocks is just m, right? Because the permutation is the full rank.
Yeah, so it's M.
Okay, so we have a vote for m. We have a vote for something with a square in it.
No, I meant for the W stochastic.
Oh, yeah, no, the rank of our binary blocks is just m.
So I mean, so probably M minus 1 times M minus 1, if it's consistent.
Interesting. So yeah, so we got a lot of different ideas. So here's a clue. So let's say I have a collection of maps here. We've got all kinds of birds, bluebird, cockatiel, toucan, big bird. I map all of them in between. Remember that if my maps are consistent, then I can take any block of this matrix, and I can write it as like the map into shape 1 and then back out. Right? So in other words, let's see if we can kind of translate that into math a little bit. For any block xij, this notation here is going to be like the block corresponding to the map from I to j. I can always write it as the map from I to 1 and then from 1 to j, right? So in other words, let's see. I guess it'll be I to 1, 1 to j, like that. You can see why the indices are annoying to get right. And by the way, just to make things even simpler, of course, this is J1 transpose. So in other words, if I have the first row blockwise of my matrix, so really the first m rows of S, then I have the whole matrix, right? I can reconstruct any other entry here just using the first row here. Does that make sense? Using this formula. So what does that indicate the rank should be? Dustin's got it. He just doesn't want to say it.
Small m. Like
Should be m. That's right. The rank of this big matrix X should be small m, and the reason is exactly this relationship here. And in fact, that gives you a factorization of big X, right? That I can write it as a product of these two things. These are both rank m. We argued that before. So this is the product of two rank m matrices like that. So we get a rank m X. Does this argument make sense to everybody? You're all very quiet. Any questions? No? The rest of this lecture is going to be real boring if you don't get this argument. Yes?
the large matrix big M doesn't have to be of full rank, right? In that case.
That's true. Yeah. So remember that part of our definition of a map matrix is that it's binary. But if I got rid of constraint 1, you're absolutely right. Then you'd have to worry a little bit about the rank of the blocks. Yeah. In fact, then it's not so clear what cycle consistency means for that matter. Like, you can no longer have this transpose. You need an inverse, right? Yeah. Any other questions? So notice we're cooking with gas here. Like we're starting to get some clues how to translate. This is like similar to a lot of other things we've done in this class, even like the Laplace operator and so on. Like we take an annoying geometry problem and then we translate it to linear algebra language because then we can like do stuff with it. And this is another good example of that. We took our collection of maps and we converted it into this set. This is like the input to our problem. And moreover, we can check if we're good because if you're rank M, then you're all set. In fact, this is an if and only if. You can convince yourself it goes the other way around. Because if you have this factorization, you have a consistent set of maps, right? Because you got it right there. Okay, so what do we want? In some sense, then, we kind of want like the most, we want the kind of rank M approximation of our input matrix, but unfortunately for us, we have all these constraints that we have to worry about when we do that, right? And that's where this problem gets really nasty. Okay, so here's kind of a fun thing. In fact, we can do better than that. And this is a surprising theorem. And you guys should be shocked and amazed by this really cool, beautiful observation that's hiding in a footnote of a SGP paper from years ago. Essentially, here's going to be the idea. We're going to define a particular notion of cycle consistency. Our temp should be his spider sense should be tingling, because we're going to be just thinking about cycle consistent maps, which are cycle consistent on cycles of 0, 1, 2, and 3. So only triangles. Under some conditions, which are articulated in this paper, that's enough to extrapolate to larger cycles, but we're not going to worry about that today. But we're going to have this definition 2.1, which is on the board here. The map is a map matrix is cycle consistent if it satisfies these 3 properties. And what we're going to show is that for a map matrix, so one of the x's that satisfies these 3 constraints, there are actually 3 different conditions that you can check, all of which are equivalent to one another. Okay? And this is a shocking theorem. This is exciting and super cool. It's really interesting that this happens. Namely, the first one is cycle consistency. The second one is just factorization, which we just kind of argued, right? Here's the third one, which is really confusing, which is that if you are a map matrix and you're semi-definite, you're automatically cycle consistent. This is not obvious by a long shot, right? Because it's going to be easy enough to show this direction that 2 implies 3. In fact, it's basically just looking at you. But to go from 3 to implying anything else here is really challenging, because notice that this thing doesn't tell you anything but the rank. Yeah? And so that's what's going to be really beautiful here. And it's also somehow a really deep and fundamental observation about the set of cycle consistent maps, which is somehow the hard constraint here. So we're going to formulate an optimization problem someday to approximate a set of maps cycle consistent. And I think the sort of default thought would be, we know that that's equivalent to being rank M, and that's going to be the constraint that's hard to optimize. But this thing says that's not actually the case. You can drop that constraint. It's fine. The hard to optimize constraint is actually 1 right here. It's just the fact that your map matrix is binary. So it has nothing to do with cycle consistency, everything to do with making permutations look like permutations. This is shocking. It's really surprising that this is true. Okay, so let's try and prove this theorem. We'll see how far we get today. We'll finish it on Thursday. This one's a little messy. This is one of the more mathy lectures in this course, but good for you. We don't have a homework, so you can pay as much or as little attention as you want. Okay, but I think this is a really interesting theorem. It's so cool. I spent this morning, first of all, convincing myself my proof from the last time I taught this class was wrong, and second of all, being excited about the fact that this is true. Okay, yes, okay, Carly.
I guess I'm a little bit confused about the optimization problem. Where's the information about the actual shapes?
Right, so remember our setup is that somebody has run a mapping algorithm between every pair, but it's inconsistent. So we're kind of going to, put lipstick on a pig here, go back and repair that collection of maps to be consistent. So what you as input, you get an X that satisfies all of these constraints, but not the rank constraint. And you want the best approximation of X, which also satisfies this other thing here. We're going to articulate it more after we prove this theorem, but that's the basic setup. Yeah. Okay, so first we're going to prove a weird lemma. There are a few lemmas in this course that, for the most part, I've tried to draw pictures for you guys of what they're telling you about life, and then there are 1 or 2 that I just have never been able to do that. Mixed partials is another one. And this is one of those lemmas. But algebraically, it's very easy to prove, which is the following. So, suppose we have a real number x, then there are 2 conditions that are equivalent. One is the following: 1, 1, 1, 1, 1, x, 1, x, 1 is a semi-definite matrix, which is 3 by 3. By the way, we're going to call this M of x. So input's a scalar and output's a 3 by 3 matrix. This is true. If and only if. Anybody have any guesses? You shouldn't, because it's counterintuitive. But x equals 1. That for any other choice of x, this matrix is not positive semi-definite. Okay, yeah, weird fun fact of the day. so let's prove this little lemma. First, let's do the easy direction, which is the left direction of the implied zero. So here we have the matrix 1, 1, 1, 1, 1, 1, 1, 1. So in other words, of 1, you can write it as 1, 1 transpose, where this is the vector of all ones. Yeah, and notice that this is a positive definite matrix just because it's an outer product. Yeah, so we're good. This is the set. Okay, so now let's do the annoying direction of this proof. I'm gonna erase this one line just to buy myself another inch. Okay, so let's do the forward direction. Okay. So positive definite matrices, or semi-definite at least. There are many different equivalent definitions. The one we're going to work with today is that all the eigenvalues of this matrix are greater than or equal to 0. And this argument's only work by 3 by 3 things, because we're going to do a really ugly thing, which is just compute all of its eigenvalues as a function of x. Just because, we got time on our hands. It's almost the end of this course. I don't want to have to prepare another lecture, all that. So, in particular, suppose lambda is an eigenvalue of my matrix, okay? Then, in particular, so we're trying to prove this direction, right? So what do we know about lambda? It's an eigenvalue, and our input is that this matrix for some x is positive semi-definite. So in particular, lambda must be non-negative, right? So no that, okay? So if you think back to your undergrad linear algebra class, there are many ways to compute eigenvalues. We're going to do the impractical one that's easy to do on the blackboard. Namely, we have this thing called the characteristic polynomial, where you have m minus lambda I, which is going to be the determinant of 1 minus lambda, 1, 1, 1 minus lambda x, 1x, 1 minus lambda, like that. Right? And this thing has to equal 0 for any eigenvalue lambda. So you guys remember this story? Okay. For convenience, we're going to define p to be 1 minus lambda. So in particular, if lambda is greater than or equal to 0, what do we know about p? I always get this wrong.
Less than or equal to 1.
That's right, less than or equal to 1. Okay, so this is just we're just moving the eigenvalues around to avoid the minus signs here. Okay, so this is determinant p1, 1, 1p x, 1x, okay, like that. And now we do our favorite eigenvalue formula. What is this thing going to be? It'll be p times p squared minus x squared. Then we have a minus 1 times p minus x, like that, plus a 1 x minus p, like that. Hopefully I did that right. Okay. And presto changeo, if we do a little bit of algebra here, what is this equal to? Well, we've got a p cubed here. Then the coefficient of p, we have an x squared there, a minus 1 and another minus 1. So this is p plus 2x, right? We have plus x and another x. Okay. Have I managed to make a mistake yet? I don't think so. Okay. So, anybody want to guess the roots of this thing? I couldn't. So when I was, if it's really funny if you, this lemma is stated in the original research paper as trivial, but I kind of struggle with that. I had to do it by hand. Yes.
So actually, I think there's a
Did I make a
simple
mistake?
solution to the first thing. So we just compute the determinant.
Uh-huh.
I think it is negative x minus 1 squared,
Mm-hmm.
but the determinant is the product of eigenvalues. So if it's something, if it's something else than 1, it is negative, so it has negative eigenvalue.
Right. So you could compute the determinant. That would be the product of the eigenvalues. Then but that.
And it is negative x minus 1 squared.
Okay. So we're gonna have. Let's play along. It could easily be that there's an easier proof. So you're saying this thing is that.
Yeah, and unless x is 1, this is negative, so there is negative eigenvalue.
Oh, I see. Okay. Yeah, you're right. So never mind. Yeah, this is a much easier proof. Okay, let's do the proof that we suggested. Sorry. Yeah, good point. Okay, great. I'll fix my notes for next week. That's funny. That's not what these people suggest to do. But you're absolutely right. That's dumb. I should know that. Okay, so here's a better proof. So, well, for one thing, we know that it's the product. Let's see if I managed to get your argument right. Of all three eigenvalues of our matrix, and because we are assuming that it's positive semi-definite, what do we know about the product of three non-negative values? You're killing me. Yeah, it's greater than 0. Okay, that's right. So, like, what is this determinant? Well, let's see. We've got 1 times 1 times 1 minus x squared. We have a minus 1 minus x, so plus 1 minus x. And then we have plus x minus 1, like that. Did I do that right? You're nodding, but like unlike most things, this is not in my notes, so there's a likelihood of a mistake. What was that?
I think the third and fourth thing are swaps.
Oh, you're right. So that should be that. And then we have plus x minus 1. Yeah, that looks right, I think. Okay, so what is this thing? We have a 1 minus 1 minus 1. So minus 2 minus x squared plus 2x, like that. Is that right?
Maybe -1 instead of -2.
Wow, I got 2 minus 1s here?
But you also have a +1, right?
Oh, you're right. Yeah, look at that. Okay. This is minus x minus 1 squared. Is that right? X squared plus 2x. No, that's not right. No, because there's a minus here, so you get a minus. No, you're right. I'm sorry. I'm old and tired, and it's been a long week. Yes, that's right. So what do we know? This thing is greater than or equal to 0. Okay, how do we make this thing greater than or equal to 0? In particular, x is equal to 1. Right? Anything else is going to be negative. Thank you. Much better proof. Yeah. Despite my lack of arithmetic skill. Okay. Good. All right. So you saved me a minute. Fantastic. So, despite my mumbling and aborting on a proof midway through, does this we all agree this one's correct? Fantastic. Many thanks for simplifying my notes here. Okay. So, I'm going to erase our lemma because I think this is an easy one to remember. So, anytime we have a matrix that's almost all ones, we can fill in the last one. That's what this is saying. Okay. So you think I was bad proving this thing, and then wait till we do the actual result. Okay. All right. So now let me grab this. So remember we have these three conditions. We want to show they're equivalent. So we need to show like 1 implies 2, 2 implies 3, 3 implies 1, or any whatever your favorite graph is on three things. Okay. So first of all, let's talk about 1 implying 2. So this is, if you are cycle consistent, then you can be factored, and that was what we just argued in a previous slide. So we will put our victory mark there. All right. Next, now let's do 2 implies 1. Right? So now, what do we know? We know that two things, actually. We know that we can factor x as like this, and we also, an assumption of this theorem is that it is a map matrix. So we also know that like x has permutation blocks, right? So in particular, well, if we want to, so what do we have to do? We assume we have an x like this, and we need to check its cycle consistency, right? That's the direction we're going now. So, first of all, let's see. So we have the first phi I is equal to identity. The first property there is true by definition, right? That's part of the definition of a map matrix. So now we have phi j I composed with phi I j, like that. Okay, well, because we have this matrix factorization here, we can expand the product here, and really what are we going to get? That this is equal to like x 1j x I1 multiplied by x1 I x j1, right? Where here, these are the blocks of that Y matrix. Okay? Cool. So what are we going to do? Well, we can just re-parenthesize, right? So we can take these matrix multiplications associative, so maybe we just group it the other way around, like that. Okay. Now, this is the map from I to 1 and the map from 1I to I. Now remember that the diagonal of big X is equal to the identity matrix, right? So the product of these two things is exactly along the diagonal of this matrix product here. So this product here is just equal to identity. And now you have exactly the same thing again. One, the map from J to 1 and the map from 1 to J. And so then when you multiply those two things, right, so this is equal to x1j, xj1, and this is equal to, again, identity because we're just reading off different blocks of the product. Okay? And the triplet case is an identical proof. I think we'll skip that one. Okay? All right. So now 1 and 2 are equivalent. We're happy with that. Cool so far? All right. So let's see if I can continue stalling by doing the easy directions. And then we'll do the one non-trivial one. So first of all, let's do, basically, by the way, our proof strategy is basically showing 1 is equivalent to 2, and then we're going to show 2 is equivalent to 3. Okay? All right. So let's say does 2 imply 3? Now, this is basically true just by the way that this formula is written, but just in case you didn't believe me, let's say I take a vector z, and I conjugate it around x like that. Right, because I'm trying to check if x is positive definite, if x can be written in this fashion, right? So in particular, this is z transpose y z, which is the same as the norm of y times z squared, and squared norms are greater than or equal to 0, so our matrix is positive definite. Cool? Right. So notice basically what have we argued so far? We've argued that basically this entire statement is trivial except that 3 implies either of 1 or 2. Right? That's the one piece that we're missing in our puzzle. With me so far? Yes.
For the proof of 2 implies 1, you said that the proof for cycle consistency in 3 is basically the same as 2. Is 4 also basically the same?
It is. Yeah.
So
So far the 3 versus 4 case doesn't matter, right? Yeah. That's also great. They all basically do the same thing. You just kind of collapse from the inside out. Yeah.
So the 3 versus 4, that hasn't come up yet.
Hasn't come up yet. And in fact, I guess from that argument here, it's kind of unnecessary, right? But yeah. Okay, so we've taken care of all of our easy pieces. We're left with one thing, which is if x is semi-definite, then it actually has this low-rank factorization. And that's going to be this byproduct of the fact that we know a little bit more about x, namely that it's binary, has these blocks, and that each of the blocks is doubly stochastic. That's what we're after. Okay. So, we have 15 minutes. Can we do it? I think we can try. I've never got myself in trouble rushing through a proof before, so what's the worst of that? Okay. So in particular, we're going to show the following: that 3 implies 2. Which is everything we're going to need for this technique. Okay? So, suppose X is a semi-definite matrix is a pairwise map matrix. So it satisfies the 3 conditions up here. Okay, right? So now we need to show that X satisfies condition number 2. So we're going to make a few definitions. Namely, we're going to make a matrix big D, which is going to be block diagonal. And it's going to be the block diagonal matrix of identity, x12, x13, x1n. So this is a matrix that has little n by n blocks on the diagonal, which are the map from each of the shapes into shape 1. Make sense? Or actually, sorry, the other way around, in 1 into each of the shapes. Okay. Now, we're going to define x prime. It's going to be equal to dx d transpose, like that. And remember that D transpose is the same as D inverse, right? Because the transpose of each of these guys is just their inverse. That's what Matthew argued for us before. Okay, so what does this matrix kind of look like? So remember, these are like the shapes in the maps in and out of shape 1, right? So if we think about the entire first row and first column of this matrix, then essentially by multiplying by these D's, what we're going to end up with, so this matrix is all just a bunch of identities. In the first row and the first column. Okay? And that's just by virtue of you, like essentially we've designed this thing. Its job in life is just to cancel out exactly that. Okay? Moreover, what is going to be the diagonal of this matrix? Well, remember the diagonal of X is a bunch of identities. And now the diagonal here gets multiplied by like x13 and then x13 transpose. So you're nodding, so we know what it's going to be. It's a bunch more identities, that's right. So we know a lot about this matrix. It looks like that. We just don't know what happens in these pieces. Okay? All right. Incidentally, by the way, the blocks of this matrix are easy enough. This is xij prime, and that's going to be equal to x1i, xij, x1j transpose. Do you see that? Because the D transpose is like this piece, and then this is just reading off that entries of X. With me so far? Notice this is index hell. It is so easy to get wrong, like what direction the maps are going in, and flip the two indices. And that's why I have these notes I'm following very carefully. I'm saving you guys the excruciating pain that I had this morning. Okay, so, right. So, in particular, if X is semi-definite, hopefully we can all agree that that means that X prime is also semi-definite. Right? So at least we know that. All right. So one thing that we can do to a matrix is compute its principal submatrices, which is a fancy linear algebra phrase. In case you forgot, what that means is I'm going to give you like three indices, for example, for a 3x3 principal submatrix. And I'm going to take row 5, 19, and 23, and column 5, 19, and 23, intersect those three, and just get that 3x3 submatrix. So in other words, like, I'm going to kind of draw lines like that, and then just keep these entries. Okay? So this is like extracting a row and then a subset of columns from that thing. So in particular, if X prime is semi-definite, then all of its 3x3 principal sub-matrices are also positive semi-definite. Okay, so in other words, we can kind of extract sub-matrices from these things as also positive definite. By the way, if you're not clear how to argue that, it's pretty straightforward. You can to conjugate one of these is the same as conjugating that with a matrix with a vector that's like patterned with a bunch of zeros. Yeah.
Sorry, I wasn't sure why X prime was positive semi-definite.
Oh, why this one it should be? Sure. So let's take vector z transpose x prime, which is dx d transpose z, like that. If we parenthesize this way, we can call this thing, I don't know, z bar.
Okay.
So this is z bar transpose x z bar.
Okay.
And x is positive definite, so that's what it's. Cool. All right. By the way, I mumbled my way around what I mean by submatrix. So just in case you weren't familiar, like let's say that I did a 2x2 submatrix of A, B, C, D, E, F, G, H, I, and I did like 1 and 3. Then I would just take rows, columns of 1 and 3, and that would lead me to like what? A, C, G, I. You guys see what that construction is doing? So it's just like extracting a subset of rows and columns. It's easy enough to check if this is positive definite, all these guys must be too. Okay. We're at the end of the course, so now we get to do the weird math. Okay, so let's do like a bit of a schematic picture. I'm going to try and draw a suggestive picture, and then we're going to see if we can kind of fudge our proof out of this thing. So we have our X prime matrix. It's got a bunch of blocks in it. that. Okay, and so far we've argued that there's like a bunch of identities here and there. That's our schematic so far. This picture kind of makes sense of what I'm saying. Okay, so now we're going to choose a principal submatrix. So we're going to like target 3 rows and 3 columns, the same index. And we're going to assume that j is equal to I plus m times a constant. And then k is equal to I plus m times another constant. So in other words, like, if I do vertex 5 of shape 1, then I have to look at vertex 5 of shape 23, something like that. That's what this is saying. Okay? So we're going to extract a 3 by 3 IJK submatrix. And what is this matrix going to look like? Okay. So let's think about elements. So we've got IJK, IJK, and we're doing the same thing here, like that, like that. Okay? So, what is element II of my matrix? 1. Right? That comes from the fact that this whole thing has diagonal equal to 1, right? Okay. You can probably see where we're going to go with this. Whereas, what's element JJ?
1.
Or Tim, what's element KK? 1. Thank you. All right. What's element IJ? So we're going to make one more assumption, which is that I is going to be in 1 to m. So it's specifically in the first shape. Now, why do I do that? Well, remember that we know slightly more about the first row. It's just a bunch of identity matrices. Okay? So, what's element IJ? I'll kind of draw the picture here. Let's see if I can kind of draw that intersection the right way. What number do we think should go here? Zoe, where should I put in this element? 1. Thank you. Similarly here, similarly here, similarly here. What was that?
Just like we recently got the lemma here. We just got the matrix that was proven in the lemma.
Yeah, that's right. We were only missing 2 elements of this matrix, and we happen to know that it's semi-definite. So in particular, we know that x is equal to 1. Namely, we have filled in all of these other off-diagonal blocks. Almost. Notice that essentially what we've shown is that the diagonal of each of these rectangles has to be 1. But remember that our condition for being a matrix is that your block doubly stochastic. And the only doubly stochastic matrix whose diagonal is equal to 1 is the identity. Okay? So, what did we just show? Like, we have to kind of like back our proof out a little bit. So, we have this giant matrix. Essentially what we've shown is that x prime is really boring. You see that? In particular, xij prime, every single block of x prime, what did we just show? Is equal to the identity, right? Because we just filled in all those missing squares there. Does that make sense what we just did in this proof? Isn't that sneaky? Okay. Now what is xij prime? Remember that's equal to x1i, xij, x1j transpose, like that. And remember that these are permutation matrices. So Matthew, what is going to be their inverses? They're transposes, that's right. So in particular, I can say xij is equal to x1i transpose x1j. Did we do it? So, what does this show? Well, so remember we started by just assuming that x is positive semi-definite. And based on that, we showed that x actually admits to this factorization. But how big is each of these blocks? This is just basically the first row of our matrix. So really, we just justified exactly factorization number 2 here. Isn't this cool? This is a cool little lemma. right? So like, in order to be cycle consistent, it's just enough to check positive definiteness. Notice this is different than your homework. In your homework, positive definiteness was like a relaxation, right? You started with the problem, and then like this is a way to make your problem easier, but like maybe you got it wrong. That's not the case. Here, this is equivalent to the other two. We have not made any approximation at all. Isn't that cool? This is so cool. This is a really cool fact. I like this fact. Okay, so in our negative 2 minutes, let's just justify really quickly how this leads to an optimization algorithm, then we'll call it for the day. So in particular, here is the optimization problem that we wish we could solve, but we can't because it's NP hard. Namely, we have a matrix X in, and this inner product, if you think about it, is really the correlation between the approximation X that you want to be cycle consistent and the input, right? So this is the number of entries those have in common because they're binary, right? Now, what do these four conditions together tell us? Well, it tells us that it is a cycle consistent, block doubly stochastic matrix. And when we put this thing in here, it makes it binary. So this is a matrix of a bunch of permutations that is cycle consistent. First of all, this is really clean. Like it took a lot of work to show that even this non-convex NP-hard problem is an okay way to write this thing down. But it's already shocking that you can do this. So now, so to read it again, you're maximizing the number of matches that you preserve. It's binary. Every block's permutation diagonal is self-mapped. And that this is the same as the rank condition. Fortunately, this is super non-convex, so you can just replace that X is positive entry-wise rather than binary. By the way, I believe 1 and 3 are enough to make sure that X also is less than 1. But you could add that if you weren't sure. By the way, the two constraints together here are called doubly positive matrices, if you're ever stuck in bar trivia and somebody asks you. And this thing is tractable. So this is a thing that you can solve. You can code this thing in CVX. And so what they propose in this old research problem is you do this thing, and then there's a nice procedure for just rounding that matrix to a permutation. That's less important. And in fact, you can actually prove a theorem here, which is so long as some fraction of your mappings are good. Namely, it has to do with, so here, if you make a graph out of where all the edges are places that you have maps, you can actually leave terms out of this problem where you just don't have a map. Then if you look at the eigenvalues of that graph matrix, then that actually tells you the fraction of maps you could be wrong and still have this procedure give you the right solution to your problem. So in fact, for the version of the problem we covered in lecture today, it's really shocking. If you can have 25% of your matches are wrong or fewer, this algorithm, even after you do the convex relaxation, will give you a binary matrix, and it will be the correct mappings. This is really surprising that this happens. 25% is a big number. So anyway, I think we'll call it for today, and maybe we'll just finish off this discussion and talk about one more thing next time, which is a related problem of angular synchronization, and then we'll call it for the course here. But yeah, I mean, the thing that you should take away from this lecture is that A, cycle consistency is really complicated. B, there are beautiful, beautiful theoretical results that link it to all the stuff we talked about in this class, and in really subtle and confusing ways. And moreover, there are even statistical guarantees on these kinds of algorithms that say that they can behave well in practice. Okay, so with that, I will see you guys on Thursday. I hope your projects are going well. And that's all. Okay, let me stop recording. Oh, looks like my laptop stopped recording a long time ago. Uh-oh.